What if the most advanced survival system ever used in human history wasn't discovered in a laboratory, but was growing silently outside in a frozen forest? In a place where temperatures drop far below -20 degrees Fahrenheit, where wind doesn't blow but cuts through anything it touches, and where exposed skin can begin to freeze in just minutes, survival stops being a question of comfort and becomes a question of physics. Every breath carries risk. Every movement demands energy. The body struggles to replace. The landscape itself feels less like geography and more like pressure, an unrelenting force pressing down on anything that dares to remain alive within it. And yet, within this extreme edge of the world, there exists a paradox that modern survival science still struggles to fully explain. Entire indigenous civilizations across the North American plains and subarctic frontiers didn't merely endure these conditions as occasional hardship. They built entire ways of life that functioned inside them. Season after season, generation after generation. Not with metal tools that could fracture in the cold. Not with industrial systems designed to resist nature. Not with machines meant to dominate the environment. But with something far more ordinary at first glance: wood. And the deeper modern research, archaeology, and ethnobotanical studies go, the more unsettling and extraordinary the pattern becomes. What once looked like simple survival begins to resemble something far more advanced: a coordinated system of ecological knowledge, a material science built from observation rather than invention. A technology that was never written down, but lived through behavior, timing, and memory. Which raises a question that refuses to fade. How did something so fragile in appearance become the foundation of one of the most sophisticated cold environment survival systems ever developed? Because once you begin to understand what they understood, the entire perception of the landscape changes. The forest stops being background. It stops being scenery. It stops being just trees standing against the wind. Instead, it reveals itself as something entirely different. A structured network of materials. A seasonal archive of usable energy. A living system of patterns waiting to be interpreted. And at that point, one realization becomes unavoidable. The forest was never just a forest. It was a system waiting to be read. The frozen plains of North America are not simply cold. They are structurally hostile to biology in almost every measurable way. Wind does not just move across the land here. It strips heat directly from exposed skin, accelerating hypothermia faster than the body can replace lost energy. Snow reflects nearly all available light, creating a disorienting visual field where depth perception collapses and distance becomes unreliable. The air itself, dry and sub-zero, pulls moisture from the lungs and skin with constant pressure, turning every breath into a controlled struggle for warmth. In modern cold climate engineering, these conditions are classified as high-risk hypothermic environments, zones where survival depends on equipment, insulation, and precise thermal management. And yet, long before modern science defined these limits, indigenous nations such as the Cree, Lakota, Blackfoot, Ojibwe, and many other plains and subarctic communities lived within this same environment season after season, generation after generation. Not as visitors, not as survivors of rare emergencies, but as inhabitants of a system most would consider unlivable. This contradiction forces a deeper reevaluation of what survival actually means. Because if life persists here where probability suggests it should fail, then survival cannot be random or accidental. It must be structured. It must be repeatable. It must be designed through knowledge embedded in practice, material, and timing. And in environments where nothing is guaranteed, design always begins with one constant that remains available across every season, every storm, and every temperature shift. The forest edge, not as background, but as the only stable interface between life and extreme cold. Modern observers often describe forests as ecosystems, defined by biology, cycles, and interdependence between species. But within many indigenous knowledge systems, the forest was understood in a far more functional way. Not as a passive environment, but as an informational network. Every species carried predictable mechanical behavior under environmental stress. And these behaviors were not abstract ideas, but observable patterns repeated across generations. Birch responds to deep cold by naturally separating into thin layered sheets, making its bark uniquely adaptable for wrapping, insulation, and containment. Pine concentrates energy in dense heartwood while producing resin, a protective chemical response that seals damage and resists decay. Willow maintains tensile flexibility even under freezing stress, bending without structural failure where other woods would snap. Spruce and cedar preserve structural integrity while actively resisting moisture intrusion and long-term decomposition. These were not treated as random traits or isolated observations. They function more like long-term environmental datasets, accumulated through continuous generational interaction with the same land, the same seasons, and the same survival pressures. Ethnobotanical research today confirms that indigenous harvesting systems across the plains and subarctic regions were often highly selective and precisely timed. Bark was gathered during peak separation periods, when natural layering allowed clean extraction without damaging the tree. Resin was collected during metabolic stress cycles, when trees produced the highest concentrations of protective compounds. Flexible wood was chosen during sap-active seasons, when internal moisture made bending possible without fracture. This is the point where survival begins to shift its meaning, from instinct to system. Because once materials are no longer random, but predictable in behavior under specific conditions, they stop being just resources. They become engineered components. And when nature can be read with that level of precision, engineered from timing rather than manufacture, it changes everything about what humans are capable of building inside it. In modern material science, birch bark continues to attract attention for its uniquely layered microstructure and strong hydrophobic properties. Researchers study how its natural composition allows it to resist moisture penetration, even under prolonged exposure to cold, wet, and freezing conditions. But in survival environments, these same properties move beyond academic interest. They become critical thresholds between stability and failure. Even when saturated with moisture or locked in sub-zero temperatures, birch bark maintains remarkable structural integrity. This resilience is largely attributed to naturally occurring compounds such as betulin, which contribute to its resistance against decay, microbial breakdown, and water intrusion over time. Within indigenous survival systems across the northern and central plains, these properties were not theoretical. They were applied directly in daily life with precision. Waterproof containers were formed from layered bark sheets, allowing secure storage of food during long winters. Emergency fire ignition surfaces were created from thin, resin-rich strips that could catch flame even in damp conditions. Insulation layers were integrated into shelter construction, helping stabilize internal warmth against extreme external cold. Lightweight transport wrappings preserved dried meat and fish, protecting vital nutrition from moisture and spoilage. But among all its uses, one function stands above the rest in terms of survival impact: its energetic behavior. Because birch bark contains volatile oils that allow it to ignite rapidly, even when exposed to moisture or freezing air. In environments where everything is damp, frozen, or resistant to combustion, this becomes an essential advantage. In extreme cold systems where ignition failure is not inconvenience but mortality, the ability to produce flame on demand becomes a form of time-sensitive survival engineering. Every second without fire is a measurable loss of core body temperature. Every failed ignition attempt increases physiological risk. And yet birch, as powerful as it is, represents only the entry point into a far more complex survival architecture. Because fire alone does not sustain life. Heat must persist. Pine behaves differently from most temperate trees. Where many species respond to extreme cold with structural fragility, pine develops internal density and chemical stability that allow it to remain functional even under harsh environmental stress. Its heartwood is tightly compacted, enabling a slow and controlled oxidation process when burned. This results in a sustained heat output, making pine a reliable long-duration energy source in survival conditions where consistency matters more than intensity. But the true innovation of pine is not found in its wood alone. It is found in its resin. Pine resin contains a complex mixture of antimicrobial compounds and high-energy hydrocarbons, giving it a rare combination of protective and energetic properties. Within indigenous survival systems, these characteristics were applied across multiple domains simultaneously. It functioned as a wound sealant, helping prevent infection in environments where medical resources were non-existent. It served as a waterproofing agent, sealing seams in footwear, tools, and transport materials against snow and moisture intrusion. It acted as an adhesive in composite tool construction, binding wood, bone, and fiber into durable functional systems. And it created protective coatings that slowed degradation from constant exposure to freezing wind and moisture. In some ethnographic accounts, resin was also used in oral practices during extended cold exposure, where chewing small amounts helped maintain moisture and comfort in extremely dry air conditions. From a systems perspective, pine cannot be reduced to a single material category. It operates simultaneously as a chemical defense system, protecting against biological decay and infection. It functions as a thermal support material, contributing to sustained heat production through combustion behavior. And it acts as a structural reinforcement agent, enabling durability in tools, shelters, and equipment under stress. This transforms pine from a simple natural resource into a multifunctional survival platform embedded within the ecosystem itself. But survival in extreme climates is never static. It is not defined by a single material or isolated advantage. It requires continuous movement across terrain that, under normal conditions, should halt all human progress. And it is within that challenge that the next layer of the system begins to reveal itself. In frozen environments, rigidity is not an advantage. It is a failure point. When temperatures drop far below freezing, materials that lack internal flexibility begin to fracture under even moderate mechanical stress. Every step, every load, every impact becomes a potential structural collapse. In this context, survival depends not on strength alone, but on controlled deformation. Willow solves this problem through its unique biomechanical flexibility. Its internal fiber structure allows it to respond to heat and moisture by realigning rather than breaking. Instead of resisting force until failure, it distributes stress through gradual bending and elastic recovery. This makes it one of the most important natural materials in cold environment engineering systems. Indigenous technologies across the plains and subarctic regions were built directly upon this property. Snowshoe frames were constructed to exploit willow's ability to maintain shape under repeated load cycles, enabling efficient weight distribution across deep snow surfaces. Binding systems for sled structures relied on its flexibility to maintain tension without snapping under vibration and impact. Fish traps used underwater willow frameworks that could flex with current pressure while retaining functional geometry. Even shelter designs incorporated willow skeletons that absorbed wind load rather than resisting it directly, reducing structural failure during storms. Among these applications, snowshoe engineering represents one of the clearest examples of applied physics in traditional technology. By increasing surface area, body weight is distributed across a larger contact zone. This reduces pressure per square inch to levels below the structural collapse threshold of snow, allowing movement across terrain that would otherwise cause complete immobilization. Different regional designs demonstrate environmental calibration rather than uniform construction. Narrow frames were optimized for deep forest conditions, allowing penetration through layered snow and dense terrain. Wider frames were adapted for open plains, where wind-packed snow required maximum surface stability and drift control. This is not random adaptation. It is a precise response to environmental variables shaped through long-term observation. A form of engineering without written equations, but governed by consistent physical outcomes. And once movement across frozen terrain becomes possible, the next limitation disappears. Because survival is no longer about staying in place. It becomes about sustaining life in motion. Indigenous shelter systems across the plains and subarctic regions are often mischaracterized as simple or primitive structures. But when examined through the lens of environmental engineering, they reveal something far more advanced. In reality, these shelters function as passive thermal regulation systems designed to maintain internal stability without external energy inputs beyond controlled fire use. The Wickiup is a clear example of this logic. Its dome geometry is not accidental. It is engineered to deflect wind pressure across curved surfaces, reducing direct structural impact. Layered bark insulation traps internal heat, creating a stable thermal envelope that resists rapid temperature loss. Controlled smoke ventilation systems allow airflow balance, preventing suffocation while retaining warmth. Pit houses extend this principle even further. By embedding the structure partially into the ground, they utilize the Earth's thermal inertia, where soil temperature remains more stable than surface air. This creates a buffering effect that smooths extreme temperature fluctuations and stabilizes internal living conditions over time. TP structures introduce another layer of environmental intelligence. Their conical form generates predictable airflow dynamics, allowing smoke and heat to rise efficiently through adjustable openings at the top. This creates a self-regulating system where ventilation and warmth are continuously balanced through simple structural design. Across all these variations, a consistent principle emerges. The structure does not resist the environment. It stabilizes within it. And within this architectural logic, fire is not just heat. It becomes the central regulating force that brings the entire system into equilibrium. Fire in extreme cold environments is not simply combustion. It is a controlled thermal system, governed by material hierarchy and precise management of energy flow. Within indigenous firecraft systems, fuel is not treated as a single category. It is organized into functional layers, each with a specific role in ignition and sustainability. Tinder forms the ignition base. Materials such as birch bark, fungal fibers, and dry plant matter provide highly reactive surfaces capable of capturing the first spark even under damp or freezing conditions. Kindling serves as the transition layer. Cedar and willow twigs allow the flame to stabilize, bridging the fragile ignition stage into sustained combustion. Primary fuel represents long-duration energy. Dense woods such as pine, tamarack, and hardwood logs maintain steady heat output over extended periods, ensuring thermal continuity in freezing environments. Ignition itself is achieved through multiple engineered methods. Friction-based bow drills generate heat through mechanical rotation, converting motion into ignition energy. Mineral-based spark systems, using stone impact, provide alternative ignition pathways when organic friction sources are limited. But the true innovation lies beyond ignition. It is in system management. Fire is not allowed to behave as an uncontrolled event. It is maintained as a semi-stable energy source, carefully regulated over time. Heat-retaining stones are positioned around the fire to absorb thermal energy and release it gradually, functioning as primitive thermal batteries. Ash layers are preserved deliberately, insulating embers overnight and allowing reactivation without full reignition. Fire placement within shelters is strategically designed to optimize airflow, heat circulation, and structural warming efficiency. This transforms fire from a temporary reaction into a continuous system, a system that supports not only immediate survival under extreme cold, but long-term continuity of life within it. And continuity, in its most fundamental form, always requires one final layer: storage. In extreme winter environments, preservation is not a secondary concern. It is equivalent to survival itself. Without stable food storage, energy loss accelerates faster than any human body can compensate for. In these conditions, time becomes the most dangerous variable. Indigenous food systems solve this through a dual-layer preservation strategy that combines environmental freezing with controlled smoke dehydration. Meat and fish are carefully sliced into thin sections to increase surface area, then wind-dried in cold air until moisture content drops to levels that inhibit bacterial growth. Smokehouses are used to regulate microbial activity further, maintaining low, controlled heat exposure that stabilizes preservation without cooking the food completely. At the same time, birch bark containers function as natural insulation systems, protecting stored food from temperature fluctuations and external contamination. But these systems extend beyond nutrition. They integrate directly into medicinal knowledge systems as well. Willow bark contains salicin-based compounds that provide natural pain relief, functioning as an early biochemical analgesic. Pine extracts are used for their antiseptic and respiratory supporting properties, particularly valuable in cold, dry air conditions that strain the lungs. Cedar smoke is employed to purify indoor air environments, reducing microbial presence and improving overall sanitary conditions within enclosed shelters. Ethnobotanical research confirms that many of these naturally derived compounds align closely with modern pharmacological classifications, revealing functional parallels between traditional knowledge and contemporary science. This demonstrates a key structural principle. Survival systems were never isolated functions. They were integrated networks operating across food, health, shelter, and mobility simultaneously. Each component reinforced the others, forming a continuous survival loop. And when viewed as a complete system, all of these layers converge on a single foundational relationship: the forest itself. Across all survival domains, one principle remains constant: nothing is taken without return. Harvesting cycles align with regeneration cycles. Deadwood is prioritized over living trees. Ash returns to soil systems. Even tool creation is guided by material respect thresholds. This establishes a long-term ecological feedback loop. Human survival depends on forest continuity, and forest continuity depends on human restraint. This is not mythology. It is ecological engineering based on reciprocity, which leads to the final realization: the forest was never a resource. It was a partner system that only functioned when balance was maintained. Modern survival science often focuses on technology, but some of the most effective systems in human history required no machinery at all. Only observation, only adaptation, only respect for what already existed. This is Dark Origins, where history is not simplified, but re-examined through the intelligence it once contained. If this journey changed how you see the natural world, stay with us, because the next story may not take place in the past, but in the knowledge we are slowly learning to remember again.